So the first question we asked in my lab, what is the effect of insulin on the nature of adipose tissue? We increased insulin, and if we increase insulin, what's going to happen to ketogenesis and ketone levels? Of course, it's going to plummet. First study was inducing hyperinsulinemia in a mouse model. And what we found immediately, so let me take you through this. This figure is firstly just looking at the mass, the growth of the fat pads over this 4-week of induced hyperinsulinemia. And just like humans, mice have very distinct depots or places of fat tissue. The perirenal is a typical visceral fat. The inguinal on the mouse is a subcutaneous fat that's right beneath the skin. And then the interscapular is the mouse's site of true brown fat. And then the humans, that's sort of where we are carrying it, in our thoracic cavity. What you'll see is that hyperinsulinemia in the animals increased the perirenal, the visceral, and the subcutaneous fat, but it had no effect at expanding the overall mass of the typical brown fat, that prototypical brown fat site. And that inguinal site in the animal, as I said, is comparable to the human subcutaneous. And what's so remarkable about that is our subcutaneous fat in most people is our greatest site of fat storage. And in humans, our subcutaneous fat, as you can see from this study, that subcutaneous fat that is classically considered white can in fact start to shift over to be more brown and thus more metabolically active as it starts chewing through glucose to just produce heat.
In humans, subcutaneous is greatest site for fat storage, can become more brown when not in hyperinsulinemia.
So it's increasing the degree to which the mitochondria are uncoupled. It's pulling apart the need to use energy just for the sake of getting work done. Now, then we looked at what insulin was doing to the actual effect, to the mitochondrial physiology. And so in this case, I'll just simply state these two figures that you see on top and bottom in the middle of the screen. This is us actually looking at the rate at which the mitochondria are using oxygen. This is metabolism, if you will, in its purest form, the degree to which mitochondria are using oxygen. And so you'll see that in the white adipose tissue, insulin did nothing to the mitochondria. There was very low rates of respiration. The mitochondria in the white adipose tissue were already using very little oxygen, and insulin didn't do anything to it. And then further to the right of that, you'll see UCP1. This is us actually measuring the amount of that UCP1 protein. And you'll see that it's a big blank space all across. There was no effect. It was already very little or almost undetectable, and insulin didn't do anything to it, good or bad, from what we could tell. In contrast, when we looked at what insulin was doing to brown adipose tissue, we saw, as you can see, the black bars compared to the white bars in that bottom figure, insulin brought down the degree to which the mitochondria are using oxygen. And this was in brown fat tissue. This is a tissue that is designed to have a high rate of mitochondrial respiration. And if you look a little further, you'll see the first two in uncoupling of the UCP1. The animals that just got the PBS injections, that's just a control, a saline solution. They had high levels of uncoupling protein in their brown fat. And then as you go over to the right a little bit, you'll see that is greatly dropped. The uncoupling protein was just plummeted in the brown fat tissue in these hyperinsulinemic animals. Then we looked at the actual metabolic rate. We put the animals in metabolic chambers and measured what's called indirect calorimetry. And we found that over 4 weeks, that at the beginning both animals had comparable levels of respiration rates or of metabolic rate. And then after 4 weeks, the insulin brought that metabolic rate down significantly. This is overall suggesting a shift, that the brown adipose tissue is starting to behave more like white adipose tissue. Thus, we start to see an overall shift where we're promoting an environment, a metabolic environment, that is favoring storage and is inhibiting use, all because of insulin.
In the white fat group, the non-insulin and the control group showed no difference in mitochondrial uncoupling. In the brown fat group, the non-insulin group showed significant improvement in mitochondrial uncoupling, and its metabolic rate increased. Insulin was converting brown fat, body fat burning, into white fat, body fat storing.
Annotated and summarized. Easy to share with loved ones.
The description below the title for this video has these summary points. In this study, in Dr. Bikman's BYU lab, he was inducing hyperinsulinemia in a mouse model. The study lasted 4 weeks, and there were 2 groups, the PBS group, which was the control, and an insulin group. Perirenal is typical visceral fat. Inguinal is subcutaneous fat. Interscapular is the site of true brown fat, generally in our thoracic cavity. In the mice, hyperinsulinemia increased fat in the perirenal, which is visceral, and in the inguinal, which is subcutaneous, but did not increase brown fat. In humans, subcutaneous is greatest site for fat storage, can become more brown when not in hyperinsulinemia. This increases the degree mitochondria are uncoupled and able to burn body fat for heat. In the white fat group, the non-insulin and the control group showed no difference in mitochondrial uncoupling. In the brown fat group, the non-insulin group showed significant improvement in mitochondrial uncoupling and its metabolic rate increased. Insulin was converting brown fat, body fat burning, into white fat, body fat storing.